In the last lecture, we discussed weak convergence. We covered two modes of convergence, that is convergence in probability and convergence in the mean square sense. So these are weak convergence modes because we consider some functions. For example, here we consider the probability that xn minus x, this is greater than any epsilon, arbitrarily small epsilon. So this probability should go down to 0 as n tends to infinity. Similarly, here we consider e of xn minus x whole square. This quantity goes down to 0 as n tends to infinity. So this is the convergence in mean square sense and convergence in probability, and their interrelation also we discussed. We will now discuss another weak convergence concept, and this is in fact the weakest concept. So we will discuss about convergence in distribution. So let us see the definition. Consider the random sequence xn, this is the sequence from n is equal to 1 to infinity suppose, and a random variable x. Suppose f(x) x and f(x) of x are the distribution functions of xn and x respectively. This sequence is said to converge to x. Now this sequence is said to converge to x in distribution if corresponding distribution function sequence converges. So what does it say? If limit of f(xn) of x as n tends to infinity is equal to f(x) of x. Now this is for all x at which f(x) of x is continuous. So this is another requirement, that this limit should be equal to this for all x at which f(x) of x is continuous. And this convergence we write as xn converges in distribution to x, and sometimes it is also called xn converges in law to x. Now essentially here the distribution functions, sequence of distribution functions converges to the distribution function of the random variable x at all points of continuity. So we have to note two things. First of all, we are considering the limit of this sequence, distribution function sequence. So this limit may not be a distribution function. There is no guarantee that this limit will be a distribution function, but we will say that it is convergence in distribution only if this converges to a distribution function. For example, suppose you consider a function f xn of x is equal to 1 for x greater than equal to n, suppose is equal to 0 otherwise. So this function, now this function will converge to as n tends to infinity. So this function will converge to 0. So this f(x) limit of f(xn) of x as n tends to infinity, it will become as n tends to infinity because x when we increase that, so it will 0 will extend, so it will become 0. So which is not a distribution function. Therefore we have to ensure that this distribution function sequence converges to a distribution function. Second thing is fxn of x converges to fx of x for all x at which fx of x is continuous. That is important. For example, if we consider suppose fxn of x is equal to 0, x less than 1 by n is equal to suppose 1, x greater than equal to 1 by n. Now, if I have suppose fx of x is equal to suppose 0, x less than equal to 0, suppose x less than 0 is equal to 1, x greater than equal to 1. Now, this essentially means the deterministic function that x is equal to this essentially means that x is equal to 0. Now, if I consider this limit of this as n tends to infinity, so this will become 1 for x greater than 1, and it will, but at n is equal to, at x is equal to 0, it will be always equal to 0, unlike this function. So, for this function, for x is equal to 0, it is for x greater than equal to 1, it is x greater than equal to 0, it is always equal to 1. But at this point x is equal to 0, x is equal to 0, this is not converging, because fxn of x as n tends to infinity, at point x is equal to 0, it will become 0. So, that way this convergence is there only at points at which x is fx of x is continuous. So, at x is equal to 0, fx of x is not continuous. So, we do not bother about the convergence at that point, but any other point where fx of x is continuous, this fxn of x converges. Then we say that this sequence converges in distribution. We can consider another example. Suppose this is the PDF, that is x, all xi's are uniformly distributed. The sequence of independent random variables with each random variable xi uniformly distributed between 0 to a. Now, in this case we define a sequence fzn. So, fzn of z, now if I consider fzn of z, okay. So, what does it mean? This is that probability that zn is less than equal to small z. What does it mean? That probability that maximum of x1, x2 up to xn, that is less than equal to z. So, this is now since maximum is less than z, so each of these variables, random variables, will be less than equal to z. Therefore, this is same as the probability that x1 is less than equal to z, x2 is less than equal to z, like that, xn is less than equal to z. So, we can write like this. Now, we can use the independent property. So, that way this will be equal to probability of x1 less than equal to z to the power n. Okay. Now, this is uniformly distributed. So, therefore, we know this is 1 by a is the PDF. Therefore, this quantity, suppose this will be equal to 0 for z less than equal to 0, so less than 0 suppose. Now for z lying between 0 and a, we can write this as, because if I integrate, then I will get z by a to the power n, and is equal to 1 for z greater than a. This is the PDF. So if I now this is the CDF, fzn of z is given by this. If I do the limit, take the limit, then I will get this fz, limit of fzn of z is equal to fz of z is equal to 0 for z less than equal to a, 1 for z greater than equal to a. So therefore Zn converges to z is equal to a in distribution. Now we have considered the concept of convergence in distribution. How is it related to convergence in probability? So if xn converges to x in probability, then it implies that xn also converges in distribution to x. We will see the proof. Suppose proof xn converges in probability to x. What does it say? It says the limit of probability of xn minus x, absolute value of xn minus x greater than any epsilon, arbitrarily small epsilon, that is equal to 0. Now we will consider the second random variable. This is xn sequence, and x, this random variable. Suppose at x plus small epsilon, that is x plus epsilon, we will consider a partition. Consider this subset. Suppose I have this real line, so this is x plus epsilon. So I will consider two events, that is x greater than, this side is x greater than small x plus epsilon, and this side is x less than, this is x less than, so this is x less than x plus epsilon. So this set is this subset, and this is another subset. At point x plus epsilon, we have a partition on the real line. So now we want to find out the distribution function. So for that, let us consider the event xn less than equal to small x. This we can consider by using the total probability theorem. We can find out this probability. So considering these two partition, so this is xn less than equal to small x and x less than equal to small x plus epsilon. Union xn less than equal to small x, x greater than small x plus epsilon. So this event we have considered as the union of two disjoint events. So therefore fxn of x, we can write that is equal to probability of xn less than equal to small x. Now considering that partitions, we write that this is equal to probability of xn less than equal to small x. This is comma, that means and x less than equal to small x plus epsilon, plus probability of xn less than equal to small x, capital X is greater than x plus epsilon. So these two probability we have considered here. This is okay. Now this is a probability of joint event, probability of xn less than equal to small x and x less than equal to small x. Definitely if I consider only one event, then we can write that this is less than equal to probability of x less than equal to small x plus epsilon. Now considering this event, so we consider this event xn less than equal to small x, x greater than equal to small x plus epsilon. So this is a subset of this event, mod of xn minus x. Here we see that if I take the difference between x and xn, that will be greater than epsilon. So that way this event is a subset of this event, therefore again we will have less than equal to this probability. So therefore f action of x is less than equal to this probability plus this probability. Okay. Now what happens as n tends to infinity? We are given that this sequence converges in probability, so this term will become 0 as n tends to infinity. Therefore what we get is that limit of f action of x is less than equal to f x of x plus epsilon. So this is, that is CDF of x, and that is at point x is less than equal to the CDF of x at point x plus epsilon. Now we can consider, again we can consider a partition on R at point x minus epsilon, suppose x minus epsilon. Now we will consider the partition in terms of the random variable xn, so that xn is less than equal to small x minus epsilon and xn is greater than small x minus epsilon. So that way we can consider a partition, and in the same way we can continue, and then we can prove that f x of x small x minus epsilon, that is less than equal to limit of as n tends to infinity f x n of. Similarly we can consider a partition on the real line at point x minus epsilon involving the random variable xn, so that xn is less than equal to small x minus epsilon and xn is greater than equal to small x minus epsilon. These are the two events, suppose. So then we can show that f x of x minus epsilon, that is less than equal to limit of f x n of x as n tends to infinity. Here we showed that limit f x n of x as n tends to infinity is less than equal to small capital F x of x at x plus epsilon. So this inequality we showed earlier. Now we show that f x of x minus epsilon is less than equal to limit of f x n of x as n tends to infinity. So from this 1 and 2 we get that limit f x n of x lies between f x at point x minus epsilon and f x at x plus epsilon, where epsilon is arbitrarily small number. Therefore as n tends to infinity, this limit f x n of x will be equal to f x of x. So this says that if sequence xn is convergent in probability, it will be convergent in distribution also. Now the converse of this theorem is not true. That means convergence in distribution need not imply that convergence in probability. We consider the sample space S is equal to HT, head and tail, suppose, with probability of tail and probability of head equal, that is equal to half. Now we define a sequence of random variable, suppose xn of h is equal to 1, xn of t is equal to 0. Another random variable we define x of h, this other way, x of h is equal to 0, x of t is equal to 1. In the case of xn of h is equal to 1, here x of h is equal to 0. Now if I have to draw the distribution function of both, suppose this is n, this is x, f xn of x. Now xn of h is equal to 1, so probability of head, suppose at 1, this is the 1, and so this is 0, so up to here it will be half. So here half, and then this will go to 1 like that. This is 1. So this is the CDF of xn of s, or CDF of xn, that is, if I consider x this side, fxn of x, that at x is equal to 0, that will be corresponding to tail. So that is a half probability at 1, that is a so cumulative probability will be equal to 1. Similarly, in the case of fx of x also, if I consider this is suppose x, fx of x, here also this will be equal to, at 0 it will be equal to half, and then this is at 1, again it will be equal to 1. Okay. So now these two distribution functions are coinciding, but here we have to remember that these mappings are different. Therefore, let us see what happened to the probability of the event where x and x are different, considerably different. So that is, we consider the probability of those sample points where xn and xn minus x is absolute value of that is greater than epsilon. So for that, now let us see what is the event of S such that mod of xn xns minus xs mod of that is greater than epsilon. Now whenever S is equal to head, xn of head is equal to 1 and x of h is equal to 0. Therefore, their difference will be greater than epsilon. So head will be included here. When S is equal to t, suppose xn of t will be equal to 0, but x of t will be equal to 1. Therefore, their difference is also greater than epsilon. Therefore, t is also included here. So the probability of this set will be equal to 1. Therefore, this does not go down to 0. That means xn does not converge in probability to x. So this is a counter example which shows that convergence in distribution does not imply convergence in probability. So that way we have discussed now convergence in distribution. So earlier we considered convergence in probability, convergence in mean square sense. Now another weak concept, convergence in distribution. Also, if suppose x is continuous, this is also a theorem, but we will not prove this, just this result will state. Suppose if xn sequence is continuous and x is also continuous, and then xn converges in distribution to x. This is if and only if f xn of x, this is PDF, converges to fx of x, that is PDF of x, at almost all x. Okay. So this is a theorem. That means if xn converges in distribution, then corresponding density function also converges in the case of continuous random variables. If we consider a sequence of continuous random variables, if this sequence is convergent in distribution, then their PDFs will also converge. And this is a if and only if condition. Therefore, if suppose PDF sequence is converges, then also this sequence will converge in distribution. That means corresponding distribution sequence, distribution function sequence will also converge. Similarly, we can also write in terms of probability mass function. If xn converges, suppose if xn is discrete, so in that case and x is also discrete, then xn converges in distribution to x if and only if that probability sequence, that is probability mass function at point suppose k, converges to Px of k at all discrete k, at all discrete k. So, what does it say? That if a sequence of random variable convergence in distribution, then this convergence can be studied in terms of their PDF and PMFs. Next, we will state another important theorem without any proof. This is required when we study the application of this concept, this mode of convergence. We will study the central limit theorem to prove that it is required. So, this is the continuity theorem of convergence. What does it say? Suppose f(xn) of x and f(x) of x are the distribution functions of xn and x respectively, and m(xn) of s is equal to e of e to the power Sn of xn. So, what is it is? This is the MGF, moment generating function. So, this is moment generating function MGF. Similarly, mxs is e of e to the power sx, that is the MGF of x. Okay. So, now we have a CDF sequence and we have a MGF sequence. If this sequence mx n of s, that is the MGF sequence for xn, if it converges to mx of s near s is equal to 0 and mx of s is continuous at s is equal to 0, this is another requirement, then corresponding this CDF sequence will also converge, or in other words xn will converge to x in distribution. So, that means if we have to prove that xn is converges, if xn converges to x in distribution, then we can start with the MGF sequence. If we take the moment generating function of xn, and if it converges to the moment generating function of x at near s is equal to 0 and mx of s is continuous at s is equal to 0, then we can prove that xn converges in distribution to x. So, starting with the moment generating function, if the moment generating function sequence, that will be another sequence, if that sequence converges to the moment generating function of x, then we can assume that according to this theorem xn will converge in x to this in distribution. So, this is a continuity theorem of convergence, and this is one important result which we will be using. Let us see the interrelation between different convergence modes. We have considered convergence everywhere, of course, that is convergence for every sample point, that is a very strong sense of convergence. This is a very strong sense of convergence. So, this will imply convergence with probability 1 or convergence almost sure. So, this convergence everywhere, because this is the strongest, it will imply convergence almost sure. This in turn will imply convergence in probability, and finally convergence in probability implies convergence in distribution. There is another type of convergence, that is convergence in mean square. So, this can be considered, this neither of this may imply this. So, that therefore, this is considered independently, and this converges, suppose action converges in mean square sense, this will always imply convergence in probability, and convergence in probability implies convergence in distribution. So, that way we have considered these 5 modes of convergence: convergence everywhere, convergence almost sure, convergence in probability, convergence in distribution, and convergence in mean square sense. So, convergence in distribution is the weakest mode of convergence. Now, we will see some application of this convergence concept. We are interested particularly about two results, two important results. They are known as laws of large number, and second one is central limit theorem. So, here we have weak law of large number, strong law of large numbers. So, that way these will apply the corresponding weak and strong modes of convergence. Then central limit theorem, this is an application of the convergence in distribution. Let us summarize the key points of the lecture. A random sequence xn is said to converge to x in distribution, that is xn converges in distribution to x if limit of f xn of x equal to fx of x for all x at which fx of x is continuous. This is the condition we impose. So, that way we define convergence in distribution, and it is the weakest mode of convergence. Also, we prove the theorems. Xn converges in probability implies that Xn converges in distribution. With a counter example, we showed that the converse of the theorem is not true, that is convergence in distribution does not imply convergence in probability. Then we stated the continuity theorem of convergence. If the moment generating function mxn of s converges to mx of s near s is equal to 0, and mx of s is continuous at s is equal to 0, then fxn of s converges to fx of s, that is distribution function of xn converges to distribution function of x. So, this is one important theorem, that is the continuity theorem of convergence. Now, let us summarize the relation between different convergence mode of a random sequence, that is xn converges almost sure implies that xn converges in probability implies that xn converges in distribution. Similarly, xn converges in mean square sense implies that xn converges in probability. This in turn implies that xn converges in distribution. Thank you.